So now we're back. Now you see the grain find results, which are opened automatically. And grain find is one of the modules which provide you with very, very much information. So you get very in detailed analysis about the grains in your structure. Um, and well, you have a lot of tables you can look up here. You have a lot of different plots where you can, for example, here you see a plot of the equivalent diameters of your spheres, so of your grains. So it's just checked how close those are to a sphere, the grains, and then those spheres, the closest sphere gets an equivalent has a diameter, and that's the equivalent diameter. And then you can plot that against the sphericity. And here, for example, they are plotted in different colors, different shapes. It's just one example. Then, well, you have a lot of plots here. So um, I think one could do a single session, so 2 hours about grain find alone. And then what's also quite interesting is here all the options for grain visualization. So you can, for example, load all the grains as an index image. So every grain in a structure gets a color, for example, um, and you can compare the grains versus fitted shapes. So, for example, here you can compare them with ellipsoids, which are fitted in the structure, and much more. So I can't talk about everything in here. And what's shown on the slides, you can also export the results to Excel. I won't do that here, but just for completeness. But I will show you here again is how to load the grains as this index image. Just click here on load, click OK. Well, then GeoDict asks if the structure should be set to invisible, which makes sense here because we wouldn't see the different colors for the grains if it would be set to visible. So click on yes, and then we just minimize the result viewer. And then you can see here the identified grains with their respective colors in here. So that just about completeness, for completeness about grain find. And now we will switch to the transport properties. But first I will re-enable the visibility of the structure and disable it for the volume field, or just discard the volume field, that we only have the structure in here. And now let's go to the transport properties. I will talk about two different transport properties you can investigate in GeoDict. This is flow and diffusion. So we'll directly start with flow. All the simulation modules, you can find them here over predict. And the two modules we will work with now are FlowDict for the flow simulations and DiffuDict for the diffusion. But you can also compute conduction in your structure. You can compute deformations and the stiffness of your structure. We will do that later. You can do filtration analysis in GeoDict, so you compute the filtration properties of your structure, and many more. You can even do complete battery loading simulations with GeoDict, which is, well, quite important. So don't forget to select FlowDict here. And then in FlowDict, which is opened here in the module section, you have different solvers. We keep here with the default with a Lear solver. It's very memory efficient and fast on most structures. So for most simulations, it's just makes sense to select the Lear solver. So just select it and keep with it. Some of the other solvers might have advantages if the porosity of your structure is very, very low. But on this structure here, that's not a problem. So just keep with the default. Go to the solver options. And then the first thing we will see here is that GeoDict complains that there is no fluid in the geometry. Well, that just depends on the materials you have defined in your structure, and we didn't define a fluid yet. And for flow simulations, you have to know the fluid properties. And well, if you have no fluid in there and no properties, you can't simulate. So where do we want the fluid to be in the pore space? So we have to select a different material here for the pore space. For this, click here on pore or the material of ID 0. Then the material selector opens, and then you see all the predefined fluids in GeoDict. We just select electrolyte in here because that's the fluid we want to simulate here. But if you want, you could either use here, for example, manual materials. You can define your own fluid directly here in the solver options, or you could edit the material database and add your own materials to it. It's quite simple. It's not very complicated. So click on electrolyte, click on OK, and then here we see in green that it's OK now. We have selected a fluid and can go on. Here for the solid, the information is enough that it's solid and that no flow is in there. We don't have to select a solid material right now in this moment. Let's switch to the boundary conditions. First, we change the computation directions from Z to X, so enable X and disable Z. You can enable all the directions at once, so you get more information because flow is computed in different directions, but it takes more time to compute and we want to spend too much time in the solver here, so we select only one direction. Then for the boundary conditions, we select symmetric here in the flow direction and also in the tangential directions because our structure here is not periodic. Periodic boundary conditions are usually faster to compute, in some cases much faster. So if your structure is close to being periodic, or if you add a very large inlet or outlet to your structure, we recommend to use the periodic boundary conditions. I will just make sure that I did not forget anything. Yeah, symmetric boundary conditions and flow direction is correct. Then we can keep that. Then here under the solver tab, there's again more information. You don't need to change anything right now. What might be interesting is here the error bound or the accuracy. With that you can just select the stopping criterion for the solver. We can keep the default here, and under parallelization you can select how many parallel processes GeoDict use. The default is just select the maximal processes that are allowed, so that is either limited by your computer or by the license. In my case, it's here a limit by the computer, and it just takes all the 8 cores that I have. And under the equations, you can get some information about the equations that are solved in here, but well, we don't have to go into detail here. Click OK to confirm everything. So here, click OK. And then just click Run to start the solver. Just one quick information here. You can always see the size of your structure in voxels up here in the structure section. So the structure size is 500 times 500 times 200 voxels. which is 50 million voxels or elements. So just that you have an estimation how large the structure for the solver is here, and the structure of this size is not a problem for a standard laptop. So I just have a business laptop here, and as you will see, it would just take several minutes to solve the flow equations on this structure. Here in the iterations, you should not fear in the beginning, because the time looks quite large here. The point is just that from the first iterations, the solver can't really estimate how long it will take, and then it tends to overestimate in the beginning. So don't get fear if you see something about several hours. It will drop quite fast in the most cases, and well, as you can see here, it just went up to several hours, and now it's nearly finished. So flow solver is finished, and what you will get here is simply a permeability tensor. So just to go back and explain a bit, what we defined here was a pressure drop from the inlet to the outlet, and then the flow velocities are calculated, and based on the information between, or the combination of pressure and flow velocities, a permeability can compute it for the structure, which is a material property. So here, that's what we were interested here, the permeability in x direction. And then you get here the error bound, which is the accuracy. You might wonder why everything is red here. That just depends on the settings you selected. If I go back to the settings, the error bound is usually just set to optimize for the permeability in the flow direction. So we define flow in x direction, and then it just optimizes for this direction. And if you also select flow in tangential permeability, then the error bound is also checked for the tangential sides, and then it will get smaller here, but it will perhaps take longer to solve. So just that you don't wonder that they are so large red numbers. You can make them green, but you just need a little bit more time. Well, and then you can again visualize the flow. You can again visualize the flow in your structure, like you can do with the pores. Simply select the flow field of the direction. We have only one here. Click on load. Then you could just deselect some of the fields in here, so you have the flow in several directions, so x, y, and z, and the velocity without a direction, and you get the pressure in your structure. Click OK, and this information is loaded to GeoDict. I will just jump a bit through the slides that we don't forget anything in here. Just a moment. Yeah, and then you just, let's switch to GeoDict and close here the result viewer. Then you just get the flow velocity shown in your structure. And as before, you can again disable your structure. You can just disable your material 1, and then you get the flow in your structure. Well, just get shown the flow velocity. You could also select other volume fields in here, just by going here to the color property and select something else for the color, for example, the pressure. And then you see as the pressure drops from the inlet to the outlet. And then you can do much more here, but I think you will learn something about this tomorrow in the visualization session. So I will jump over this now. Re-enable the structure and go back to the slides. So the next thing we will do here is diffusion. In principle, if you understood how to use one solver in GeoDict, you usually also understood how to use the other solvers. So it's quite intuitive here. Go here over predict, select GeoDict, the module for diffusion, and then we simply use the simulate diffusion experiment option. Click the edit button to open the options. Then I will just check the settings that we want to define here. So you have to define a diffusivity. This diffusivity you have to define it by your own. So it's just a number you have to know. Here we just select 3 to the minus 6. And then we are already okay here for the constituent materials. We keep the electrolyte here, and in the slides it's just told if you didn't change the material, you should do it now. So if you, for example, did not do the flow analysis, so then let's switch again to the boundary conditions tab, and here the same holds as we already selected for the flow. Select the X direction, deselect Z for the same reasons. We just want to see it in X direction, and switch the boundary conditions again to symmetric. So then here important, it's the same as for the GeoDict analysis. Here in GeoDict you have to select to write the flux into a file if you want to visualize it later, which we want to do here. If you don't need it for the analysis, it's always useful not to select it because it needs time to write and it takes space on your hard disk. So if you don't need it, then just don't select it. I click OK and let the solver run now. This will take a little bit more than the flow solver. So we can already have a look at the slides that will come now. Well, after the simulation has finished, in principle, the same things hold as for all the other solvers. You get a result file, and from this result file, you can load the results, you can analyze the results. Well, and that's just what we want to do then. And here we will do a bit more, or I will just say a bit more about the visualization, what you can do in GeoDict with some simple clicks and very simple steps. And yeah, I won't jump too much in forward. We should just wait some minutes until the simulation is finished. And as you can see here, you should again not have fear from the remaining time that is shown here. It's just very difficult to estimate the remaining time based on the first iteration, even if the first iteration is not yet finished. And now you see it's dropping quite fast. So now we have 11 minutes, and I believe that it will drop again. Now you see it's just rising again because it's in the iteration and just has to see how long it will take. But we will take less than those 13 minutes that we see right now. So I move it a bit to the side. Here, if you want to have some information about the usage of your computer, you can, for example, see that my CPU is completely used at maximum capacity now, so the computer is computing as hard as it can. But I have still a lot of memory free here, and here um, the third icon just shows the hard disk usage. It's not really relevant right here, but if you want to do very large simulations, you should just keep in mind how much space you have on your hard disk. And that fully hasn't anything to do with the simulation I'm doing right now. It's just because I do a lot of simulations and work on my PC, and right now it's quite full. I would explain a bit more about GeoDict in here, but well, I can't really select all those things because it's just working. Well, perhaps a bit about the icons here. You already saw the Open Project folder icon here. We used it at the beginning. Then here the icon is for opening structures. The next one is for opening result files. So, well, you can perhaps see that this should be a result file. And then here with the disk icon, you can save structures, save screenshots, and save videos. Here you can go to the material database and edit your material database. Then you have undo and redo buttons. You can select the renderer. And here you can select the colors. And here the next ones are about the navigation in GeoDict. So here you can select several options, how your mouse is used. Here you can select the light source for the visualization and move it. And well, you have some options to select and edit objects and voxels. So here you can select voxels in your structure. And here you can select objects if you have objects in your structure. So if you use a structure which is imported, for example, from a CT scan, it's simply a voxel structure. So you have no object information about no object information in the structure. But if you generated the structure with one of GeoDict's structure generators, you have object information. For example, you have a grain structure, and the grain structure is made of spheres. And then you can select those objects here and edit them, for example, change the color or anything. So I think it just makes sense if we now make this next break here, even it's a bit earlier than planned, but if you have questions now, just ask, and we will then start after the break with the results of the simulation.